In this section, we are going to look at the critical value approach to hypothesis testing. In particular, we're going to look at one-tailed testing for the moment. So the critical value. Now this approach is a complement to the p-value approach which I discussed earlier. Now, the test statistic has Z has a standard normal probability distribution. Okay, so you would say it's a Z random variable. Okay, that's an important thing as we go forward. And again, just to be emphasize one word here, normal. Okay. Now we can use the standard normal distribution table to find the Z value with an area of alpha in the lower or upper tail of the distribution. So essentially, we're going to use the probability tables in a lot in this approach. Now, the value of the test statistic that established the boundary for the rejection region is called critical value. So let's just sort of remark on the fact that we have two values here, the test statistic and the critical value. And these are the two major components of hypothesis testing when you use this approach here. Now, the rejection rule is as follows, depending whether you're dealing with lower tail or upper tail tests. You reject the null hypothesis if the test statistic is less than the minus the critical times the critical value, minus the value from the tables. Okay, so test statistic. This is actually an easier way of. This is the test statistic on this side, and this is the critical value on this side. So here is a one-size-fits-all approach to these rules. Actually, you can encapsulate it with one particular statement here. Is the absolute value of the test statistic greater than the critical value? Greater than the critical value. Okay. If yes, you reject the null hypothesis. Okay, so that is the critical value here would be minus 1.96. So it's minus whatever comes out of the tables. But I find it easier actually just to use this approach here, the absolute value approach. For example, if you get a test statistic of minus 1.5, the absolute value of the test statistic is plus 1.5. Okay. So, but anyway, those are the rejection rules when you're dealing with critical values. So, this is a lower tail test for a population mean, and we're using the critical value approach. In this case, the critical value here, the threshold is minus 1.28. So it's minus Z of alpha. Okay, minus the quantile that it gives you an alpha level of 0.10. And this here is called the rejection region. This area here, let me color it in. I'll color it in orange. This area here is the rejection region. So if the test statistic is on the number line in this region, you would reject the null hypothesis. So for argument's sake, if the test statistic was here, if the test statistic was here, you would reject the null hypothesis, but if the test statistic was here, you would fail to reject the null hypothesis. So it's essentially, it acts as a threshold, so that critical value is the barrier between these two regions, the reject region and the do not reject region. So again, it is actually it marks the boundary, okay, between those two regions. Likewise, we can say the same for the upper tail This is the critical value up here. And again, it marks the boundary between the do not reject region and the reject region. In this case, alpha equals 0.05, and therefore the critical value will be 1.645. Okay. So steps: develop the null and alternative hypothesis. Formally state them. Specify the level of significance alpha. Now, actually, just as a quick remark, actually, in a lot of courses, if you're not told specifically what alpha level you're to use, you're expected to sort of state one yourself quite often, and usually you will go for something like alpha equals 0.05. In other words, 5% significance level. Collect the sample data and compute the test statistic. Okay. Now, when you're using the p-value approach, this is something from earlier on. Use the value of the test statistic to compute the p-value. So again, something like this. Probability of z, because it's a random variable, as I said earlier, greater than or equal to the test statistic. Now, just as a remark, actually, it would help to actually use the absolute value there, just in case you get a negative number as your test statistic. And reject the null hypothesis if the p-value is less than or equal to alpha. Okay. But when you're using the critical value approach, this is how we would determine it. Use the level of significance to determine the critical value and the rejection rule. Now, to determine the critical value means you go to statistical tables and find it. Now, I sort of touched upon the fact there that we're dealing with a lower tail and an upper tail. So the number of tails is relevant, because there's a slightly different rule if you're dealing with one tail and two tails. There's a slightly different approach. I will sort of, in this set of tests, in this set of presentations, I'll use k to represent the number of tails, rather than, usually you sort of say n for number of something, but n is sample size. Again, you should actually, in most cases, you should be looking at a large sample, something greater than 30. That'll become relevant later on. Also, what is important is the level of significance. Now, those three components are the three components you would use to find your critical value from a tables. So, statistical tables. Now, what is best here is that I will do it, because there's quite a different lot about statistical tables in inference. I'm going to do a separate presentation for that. So suffice to say, just we'll collect up those three key points, and then we'll sort of leave it there for the time being. Now, use the value of the test statistic and the rejection region to determine whether or not to reject zero. So actually, my approaching, my distilled into one single approach earlier on, is the absolute value of the test statistic greater than or equal to the critical value. Yes, reject. And no, fail to reject. So this is where we'll take an example. So I'll leave it there.